sometimes greater than equal type. And we are also talking about the right hand side parameters like B1, B2, Bm. Generally, in the linear programming problem, we assume all the right hand side parameters are non-negative, 0 or positive. So assuming 0 or positive the right hand side parameters, so we include slug, surplus, artificial variables. Generally, slug variables we consider as our basic variable, and surplus variables are not the basic variables. Also, we have the artificial variables, artificially used, so they are also called basic variable. Whenever the artificial variables are used, so these artificial variables has to be removed using the big M method. Big M method in the sense, the M is a very large positive number. We use M to drive out the artificial variables from the basis. So these artificial variables cannot be a basic variables. Okay. So if it will be basic variables, it will remain at 0 level. If it is becoming positive, we conclude that the problem is infeasible. And as you know, we are using M. This M is a problematic parameters. Why problematic? See, the linear programming problem has some objective function. This objective function has some coefficients like C1, C2, Cn. These are the objective function coefficients with respect to variable x1, x2, xn. So we do not know exactly whether they are small or big. So sometimes whenever you are selecting M, if M is very large number, it creates problem. So when you write code, and when it is small also it creates problem. Okay, because we cannot see if I am setting something like my M equal to 10 to the power 8. Okay, sometimes it is fine, for some problem it may not be fine, because if my cost coefficient parameters is always all are more than 10 to the power 8, then it will create problem. So even sometimes problem is feasible, but if you are using the large or small M, it will detect that problem is infeasible. Sometimes problem has solution, sometimes has no solution, something like that. So we like to avoid this parameters M. This parameter M can be avoided using two-phase simplex method. So the two-phase simplex method has come to the picture now. Now we like to discuss what is called two-phase simplex method. What is called two-phase simplex method? See, whenever there is an artificial variable, we use big M method to solve that linear programming problem. So in case of the big M method, as you know, we know how to solve the problem. So we formulate the objective function. So new objective function, and with respect to the artificial variables, we put some negative, some M, and that you want to, M is a very large positive number that I want to remove. So we are avoiding that big M method. We are discussing about the two-phase simplex method. This two-phase simplex method will solve the problem in two different phases. In two different phases. So what is two different phases means? There are two different objective functions we will consider. One is called artificial objective function, and another is called the actual objective function. So with respect to our linear programming problem, we'll formulate an artificial objective function that is consisting of artificial variables. So using that artificial objective function, we'll solve the problem. Then once that part is over, we'll come to the phase 2 that I'm going to discuss. Okay, you can see the slide, two-phase simplex method. Already earlier also I have said, again I have after some changes also I will give you some problem. So what is called phase 1? In this phase 1, an artificial objective function, you may name this objective function as small f, is used where we want to minimize the sum of the artificial variables. What is a value of the artificial variable? The artificial variable values are non-negative. The minimum value of the artificial variable equal to 0. If there are few artificial variables, maybe 2, 3, 4, that depends on the problem. So sum of the artificial variables to 0 means all has to be 0. Every artificial variables we want to make 0. The total sum we want to make 0. If you cannot make them 0, then we'll conclude that the problem is infeasible. Okay, so our main purpose in phase 1, we like to minimize the artificial variables to 0. We try to drive out all the artificial variables from the basis to make them 0. If they cannot be removed, that is all cannot be removed or made 0, we conclude that the problem is infeasible. If all the artificial variables are 0 in phase 1, so we say that the phase 1 is complete. We go to phase 2. So in phase 2, we replace the artificial objective function f by the original objective function z. Z is our original objective function. Generally, we minimize or maximize the objective function. So whenever you are using the original objective function, we use the last simplex table of the phase 1. Then we apply the usual simplex method until an optimal solution is found. So we'll try to operate the usual simplex method till we find a optimal solution. See, there are some problem. So if an artificial variable is there in the basis at 0 value, at the end of phase 1, it has a 0 value, but it is there. It is remaining as a basic variable. We modify the departing variable rule. How to modify? An artificial variable must not be positive from 0. That we want to keep in mind. Artificial variable has to be 0. It will never become positive from 0. So we allow an artificial variable with negative as a value to depart. This is an important point to note. So the whole table, whatever I have already discussed, I'm not going to use the whole table because it is, so we are spending extra time in the old table. So I would like to use the new table. So new table, there are two forms. One is the extended form of the simplex table. Another is the condensed form of the simplex table. And we like to use the condensed form of the simplex table. I'm repeating again. So what is called two-phase simplex method? So this is a method which is alternative to big M method. In the big M method, our main aim to remove the artificial variables. Okay, so here we are also removing the artificial variables from the basis in two different phases. First phase, we use the artificial objective function. In second phase, we use the actual objective function. So the problem has been divided in two different phases, phase 1, phase 2. Now we'll discuss using some examples how to use phase 1 and phase 2. Is it all right? Any doubt you want to ask here? I'm going to show you some problem. There we'll discuss in details. If any doubt you want to clarify, you can ask me, I will explain. Okay, thank you. Hello?
Sir, in the absence of artificial variables, we use the old method only, no sir?
If there is no artificial variables, no need of thinking about two-phase simplex method. If artificial variables are there, now there is two options. Either use big M method or two-phase simplex method. Okay. So third method is coming. We will discuss in later. So either use big M method or two-phase simplex method. So you know fully about the big M method? Yes or no?
Yes,
what
sir.
is the purpose of M? So only big M method is useful if artificial variable is there. If artificial variable is not there, directly first method, the simplex method, okay, where you have all the constants are less than equal type and right hand sides are positive. Okay, if the right hand side is negative, then you multiply minus sign, make it positive, then so less than equal type constant will be greater than equal type constant, there will be problem. Okay.
Yes.
So in case you have equally type constants, here there is option also. You can make two constants, one of them less than equal type, one of them greater than equal type, but there is no benefit, not much benefit, but you can make two in equation to one equation. You can make two in equation. So that also will serve the purpose, but it will be lengthier. Okay. So in the last class, I have sent some slides. There are some problems we are using, the condensed simplex table, some extended simplex table. In the very beginning, we started with the condensed simplex table. Okay. So that table I have replaced either extended or condensed again. But condensed a new version, but extended we are not using because we don't want to do the extra work. So in the extended table, you have all the columns like say basic variable, non-basic variables. In the condensed, we have only non-basic variable columns. Basic variables are in the row. So that is the difference. So again, I am explaining. Let us consider some example here. See, I am going to use two-phase simplex method. So in the two-phase simplex method, you can see here there are two different LP I am considering. One is maximization type, another is minimization type. One is maximization type, another is minimization type. For the maximization type problem, our objective function is, this is a three variable problem. Our objective function is maximize z equal to x1 plus 3x2 plus x3. Very simple problem. So for the second problem, that is a minimization type problem, our objective function is equal to 3x1 plus x2 plus x3. See, earlier using the big M methods, a similar problem I have considered. There were only two variables. Now I have changed to three variables. Okay. So you will find minor difference here. These problems are three variable problem. Earlier we have two variable problem, but similar method. So we are using their big M method, but here you are not using big M method. We are going to use two-phase simplex method. So in the first attempt, we'll consider LPP1. In second attempt, we'll consider LPP2. See, for the LPP1, we have constraints. What are the constraints? X1 plus x2 plus x3 equal to 10. For the, and another constant we have also x1 plus 4x2 plus x3, this is equal to 16, and it is given these x1, x2, x3 are non-negative. Okay. So later on you can see that you can take any type of constraints, no harm, but for a simple example, I am considering both the constraints are one type, let us say equality type. Okay. So first time we are considering LPP1, not LPP2. So once LPP1 is complete, then we'll go to LPP2. Okay. Is it all right? So please think there are two different problems, not one problem. So first problem, second problem. So since the problem has a common constraints, two constraints are common, so I am considering this problem. Okay. So let us consider the first problem. The first problem is like this. This is all right. First problem. And this is maximization type. Okay. The first problem is it has a maximization type objective function. And we are going to solve using two-phase simplex method. I am naming it TPS, two-phase simplex method. So because here we have two objective function we'll formulate. So one is in phase 1, another is in phase 2. Okay. This is the problem. Now with respect to problem, two different constraints, we like to introduce artificial variables. So first constraint, there is an artificial variable, let us say A1. For the second constraints, another artificial variables, let us name it A2. See, you can put Z1, Z2 also, there is no harm, but I am saying the artificial variable starts with the letter A. So I am saying it artificial variable A1 and A2, two different artificial variables. Okay, and both A1 and A2 are non-negative. So their minimum value is 0. And these artificial variables, we like to, since you are artificially adding, we like to make them 0 always at the end of the table, end of the procedure. Okay, so whether you can make it 0 or not, we'll see. So now, once the artificial variables are introduced, we'll formulate an artificial objective function that is called phase 1 objective function. So this problem you can see here. The phase 1 objective function, first phase. So the first constant is becoming x1 plus x2 plus x3 plus a1 equal to 10. Second constant is becoming x1 plus 4x2 plus x3 plus a2 equal to 16. This a1, a2 are the artificial variables. This a1, a2 are artificial variables as well as they are also known as basic variables. Artificial variable can be basic variable. Slug variable can be basic variable. Surplus variable cannot be basic variable. Please remember, I am repeating again. Slug variables are basic variable. Artificial variables are basic variables. So this, since these two are the equivalent type constants, we are introducing artificial variables a1, a2. These artificial variables, artificially we are using, but the purpose is to solve the problem. And finally, since the artificially they are added, finally we have to remove. So finally their value has to be 0. Okay, so to drive out the artificial variables, earlier you are using big-M method. Now big-M method we are not using, you are using now two-phase simplex method. What we want to do? We want to minimize, we are formulating another objective function. We want to minimize f1, let us say. My f1 equal to a1 plus a2. Now there is a question to you. What is the minimum value of a1 and a2? a1 plus a2. What is the minimum value? a1 plus a2. What is the minimum value?
0.
0. Because a1 greater than equal to 0, a2 greater than equal to 0. So their sum, see, we want to minimize. So least value of a1 plus a2 is 0. Instead of 2, there are 3 variables. The minimum is also 0. If there are say let us say n number of variables, the a1, a2, a3, up to an, they are also their sum equal to 0. We want to minimize. Okay, not maximizing. Generally, linear programming problem, whatever you are solving, all are maximization type. If there is a minimization type linear programming problem, we have to change it to maximization type. Okay, so here our new objective function is minimize f1. Minimize f1, there is nothing but a1 plus a2. But that is equivalent to maximize minus f1. Minus f1, that is equal to minus a1 minus a2. Okay, so we are going to minimize f1, that is equivalent to, so equivalently you can write maximize minus f1, that is minus a1 minus a2. Okay, this is our first phase objective function. Now, what is the second phase objective function? So we like to decide. So second, we have two different problems. You can see here. First problem we are considering now. So second phase objective function is nothing but the original objective function, that is x1 plus 3x2 plus x3. Okay, this. So here we have already clarified this first one is the first phase objective function. Second one is the second phase objective function. Okay, but the constants are common. The constants are common. After completing the first phase objective function work, then we will move to the second phase objective function. Okay, this. So now, what we are going to do? We are going to solve the first phase problem. The first problem is nothing but minimize f1, that is equal to a1 plus a2. which is equivalently you can write maxima is minus f1, that is minus a1 minus a2, subject to two constants, two equivalent type constants, x1 plus x2 plus x3 plus a1 equal to 10. So x1 plus 4x2 plus x3 plus a2 equal to 16. This is the two constants, and our artificial variables a1, a2, they are actually the basic variables. Now we are formulating this problem. You can see here, this is the new table. So this new table should be clarified now, otherwise there will be problem. See, we have a table, some extra boxes are there because these are made, using the latex file. Sometimes it's difficult to suppress the some boxes. Wherever this there is in the table itself, there are two boxes. It should be empty, so I have put star mark there. Okay, right? So number of row, number of column, I have made it same. So actually, I'm explaining. So that third last row says something about the objective function. Last row, I will explain. Okay, then last but one row, see, there are two different constants you can see here. So one constant, that is x1 plus x2 plus x3 plus a1 equal to 10. Another constant is x1 plus 4x2 plus x3 plus a2 equal to 16. See, this we are presenting in the table itself. So there are some columns you can see. So generally the columns with respect to the non-basic variables. Presently in the problem, in the first table itself, x1, x2, x3, these are the non-basic variables, x1, x2, x3. And the right hand side, b value, 10, 16, etc. These are the value of the basic variables you can see here, the right hand side value, that is xb, or you can say b, 10 and 16. Now, in the problem itself, we have two basic variables. The basic variables are a1 and a2. So you can see here, it is written there basic variable oblique non-basic variables. Basic variable with respect to row, non-basic variable with respect to column. So three non-basic variable, two basic variables. Now we have an objective function. What is that objective function? The objective function equal to maxima is minus f1. This objective function is known as first phase objective function. This is equal to minus a1 minus a2. I can add something more. 0 times x1 plus 0 times x2 plus 0 times x3. Okay. These 0, 0, 0. These are the coefficient of x1, x2, x3 respectively. See, you can see here, there is a mark here Cn. The Cn stand for coefficient of the non-basic variables for the objective function. C stands for the cost coefficient of objective function. Cn for the non-basic variable. These coefficients are 0, 0, 0. Above x1 there is 0. Above x2 there is another 0. Above x3 there is another 0. 3 zeros are there. Because we are not writing minus a1 minus a2 plus 0 times x1 plus 0 times x2 plus 0 times x3. We are not writing. So, but we can here also you can mention here that is coefficient of x1 equal to 0, x2 equal to 0, x3 equal to 0 because they are not available. And you can see here what are the coefficient of a1, a2. Coefficient of a1 equal to minus 1. Coefficient of a2 equal to minus 1. That is there in the left hand side of a1. CB stands for coefficient of the basic variable for the objective function. Coefficient of basic variables. If my objective function equal to a1 plus a2, the coefficient will be 1, 1, not minus 1, minus 1. Here it is minus a1, minus a2. So I am writing here minus 1, minus. Okay. So once it is complete, the last row of the simplex table we like to fill up. how we have got -2, -5, -2, -26, I am explaining. So -1, -1, inner product with 1, 1. How much it is? -1, -1, inner product with 1, 1. Their sum, how much? -2. -2 -0, that is equal to -2. Similarly, inner product of -1, -1 with 1, 4. Okay, so their sum equal to -5, -0, that is -5. Then with respect to -1, -1, we are saying the inner product with 1, 1, that is -2, then -0, then it is becoming -2, then -1, -1, inner product with 10 and 16, that is becoming -26. Okay, right? So is it clear? Is it clear? Are you able to hear? Hello?
Yes, sir, it's clear.
Okay. Now there is a question to you. Instead, the coefficients are 0, 0, 0. If I am writing, okay, for some purpose, the coefficients are instead of 0, 0, 0, it is 10, 10, 10. What will be the right hand side? What will be the indicator row? The last row elements? Can you tell me? Instead of 0, 0, 0, it is 10, 10, 10. What will happen to this?
Sir,
Subtract 10.
10. Wherever there is a 0, you can see above x1 there is 0. I am saying it is not 0, it is 10. x2 there is a 0. I am saying again it is 10. x3 there is a 0. I am saying it is 10. What will happen to the last row? 3 elements.
So it would become -12, -15, -12.
-12, -15, -12. Right? -12. Okay. So if it is 1, 1, 1, what will happen?
-3, -6, -3.
Okay. So if it is say -5, -5, -5, what will happen? -5. Instead of 0, 0, 0, it is -5, -5, -5. What will happen?
3, 0, 3.
Yes?
3, 0, 3.
This will be 3 plus 3, then it will be
0,
0, and this will be
3 plus
plus
3.
3. 3, 0, 3. 3, 0, 3. So if you are finding, for example, if you are finding the last 3 elements, 3, 0, 3, what is the conclusion about this table? What is the conclusion? Is it optimal?
Yes,
This
it
table
is
is optimal? Yes, this table is optimal. The table is optimal. Now, so if it is already there -5, -5, -5, we are saying the table is optimal. Now, what will be the value of A1, A2? What will be the value of A1, A2 in this table? A1 equal to
10 and 16.
10 and 16. Now, what is the conclusion? What is the conclusion?
The whole problem would be infeasible then.
Problem is infeasible. Okay, so problem is infeasible. In this way, we conclude. And what is the value of the objective function? This minus
It would
the
be
F1 value. Minus F1 is becoming
26.
-26. F1 is becoming 26. Minus F1 equal to -26. F1 equal to 26. Okay. But as I already mentioned, once it is becoming 0, then we will move to phase 2. Unless it is 0, we will not move. Okay. It is now -26. We cannot move. Okay. With this data, we cannot move. So we like to have our usual simplex operation. Okay. This table is clear.
Yes, sir.
Sir.
If there is a constant in the objective function, where do we include and how does
That constant you keep in your memory, later on you can add. Okay.
Okay, sir.
This constant, let me say 1000, the objective function value is 1000 more. It is a sincere constant. The constant will not create any problem. Okay. So that you keep in your memory. So whatever the value, if it is positive, you add. If it is negative, you subtract. Okay, that's all. If it is 0, nothing to worry. It is 0, nothing to worry. Okay. So if it is positive, you add. If it is negative, you subtract. But if it is 0, nothing to worry. Okay, that's all. Okay. So in the first table, I have mentioned. So the d you can set as 0. Okay, because since it is a linear function must have a constant term. That is the reason I am writing d. Okay, this is the first table. You can say this is initial simplex table, table 0. Now, so
Sir.
here itself, some conclusion we like to draw. So among 3 element -2, -5, -2, forget about -26. This -26, what is there in the corner? That is the value of the objective function. We need not worry about that. This has a purpose, so it will we will consider in our decision. So the -26, now we are considering anything, but there are 3 elements. All 3 are negative: -2, -5, -2. Most negative. What is the most negative element? Most negative is -5. So with respect to the most negative element, you can see here there are 3 columns. So second column, that is x2 column, will come to the picture. So we'll take the positive ratio in this manner: 10 divided by 1, that is 10. 16 divided by 4, that is 4. Now among these two ratio, we like to take the minimum ratio. Minimum ratio is becoming 10 and 4. Minimum ratio is becoming 4. The 4 is coming with respect to the 4. There is a star mark. Okay, with the 4. So the 4 is the key element. The key element is also known as P, pivoting element. Okay, so this is very crucial. And we are using condensed form of the simplex table. Why condensed? The basic variable columns are not there. If somebody want to make it an extended table, then he has to add 2 more columns, one with respect to A1, another with respect to A2. Okay. So if he is adding A1, then that 2 elements will be 1, 0. Okay. Then another A2, 0, 1. Okay. So that I have already told you earlier. So we are using only condensed. You need not worry about the extended table. So we are using condensed table. Okay. So see, once it is there, the key element we have decided. So x2 is the entering variable. And if x2 is the entering variable, which one is the departing variable? X2 is the entering variable, and which one is the departing variable? One will come, another will go.
A2.
See, there are 5 rooms. 2 for basic variables, 3 for non-basic variables. Okay. So in one room, one of them will stay either a basic variable or non-basic variable. Okay. So these 2 are the blocks of the basic variable, and these 3 are the blocks of the non-basic variables. Okay. We can see how many ways you can set, that is obvious, but you see these are the basic variable place and these are the non-basic variable. So x2 will come to A2 place, A2 will come to x2 place. Earlier we were writing something like -x1, -x2, -x3. Now no question of minus. Okay, no question of minus. But only you can see the cost coefficient 0, 0, 0. There is a minus sign, -1, -1, -1, something written here. So due to the positive, negative, -a1, -a2, we are writing like this. Okay. So x2 and A2. So in the next table, x2 and A2, their place will interchange. x2 will come to A2 place and A2 will come to x2 place. So if x2 is coming to A2 place, what should be the coefficient here? Wherever there is -1, it will be 0. If A2 is coming to x2 place, the coefficient x2 is 0, this will be -1. So this is the changes. These are the changes, no other change. So now see this table. So here we have put 0, -1, 0. And these non-basic variables are presently x1, A2, x3. x1, A2, x3. The coefficients are 0. There was no change. And earlier it was x2 coefficient was 0. So now it is A2 coefficient is -1. Then x3 is 0. And here in the basic variable position, A1 coefficient -1, there is no change. But here there is a change. Since x2 has come here, the coefficient is 0. Okay, this. Now we are applying the other rule. What is the rule? So in place of 4, in the next table, it is the reciprocal, 1 by 4. In the same row, so we are dividing by 4. So this will be 1 by 4. This 4 plus already 1 by 4. Then 1 by 4. 16 position it will be 4. In the same column, minus 1 by 4. 1 by 4. Then it is 5 by 4. Okay. Other elements you can compute in this manner. This is will be the 1 is becoming 4 minus 1 by 4. That is 3 by 4. And this one is coming 4 minus 1. Again 3 by 4. Okay. So the 10 position, whatever 10 is there. So 40 minus 16. 24. 24 by 4 is 6. Then similarly, in the minus 2 position, how much it will be? Minus 8 plus minus 8 plus 5, 3. So minus 3 by 4. Again, you can see minus 8 plus 5, minus 3 by 4. And this 26. 26 minus 26 will be how much? 26 into 4 minus 104 plus 80. That is 24. 24 divided by 4 with a minus sign, the minus 6. So this table you can see here. We have got a table. So again, I am explaining the non-basic variable coefficients 0, minus 1, 0. Basic variable coefficients minus 1, 0. Presently, basic variables are 1 and x1, 1 and x2. Non-basic variables are x1, a2, x3. And the basic variable value. What is the value of a1? 6. What is the value of a2? Sorry, x2, that is 4. And the objective function value is minus 6 now. Earlier it was 26. Why 26? 10 plus 16, 26, there is a minus sign. So minus 26. So here only we are adding a1, a2. So due to that, a1 equal to 6 with a minus sign. So minus 6. That's all. This is the table. So earlier we have two artificial variables. We have removed one artificial variables. The artificial variable 2 is becoming the non-basic variables. So the present value of a2 equal to 0. But the artificial variable a1 is still there. The artificial value of a1 is now 6. Say if you make both 0, then it is ideal. So we'll try to have here there is actually, I think there is a minus sign, isn't it?
Yes, sir. It is minus 3 by 4 in the last row.
Yes, minus 8 plus minus 8 plus this is actually minus 3 by 4 should be. Okay, minus 3 by 4. I will just change it. Okay, this. But you see, there is a negative sign here. Negative sign. And that is third one also negative. So with respect to this negative sign, so we will conclude that this table is not optimal. We need one iteration. Okay. So with respect to this, what is the minimum ratio? You can have here 6 by 3 by 4. That is 8. 4 by 1 by 4, 16. Minimum ratio is coming 8. So this 8 is coming with respect to what? 3 by 4. Now we will re-level in this manner. X1 will come to A1 position. A1 will go to X1 position. As a result, coefficient of X1 will be 0 and coefficient of A1 will be minus 1 in the next table. And the new table in the 3 by 4 position, it will be 4 by 3. And you divide by 3 by 4. So this will be minus 1/3 and minus 1. And similarly, in the same row, you can see here, this is 1/3. Okay, this is, so you can complete. So if you are completing, we are finding in this manner. There may be some mistakes, you can just observe plus minus sign. But I've tried to minimize the error, but still I find some errors are there. Okay, this is the table. Once you have got this table, say what is the value of the artificial objective function? What is your answer?
0.
0. 0 means the phase 1 is complete. Next question is there any artificial variables which you are treating as basic variable? Is there any artificial variables are presently basic variable? No.
No.
Our basic variables are x1, x2. These artificial variables we have removed. This artificial variable a1, a2 as well as x3, they are the non-basic variables. Okay, this. So this phase 1 table is complete. Phase 1 table is complete. Now, as you know, these coefficients -1, -1, 0, 0, 0. These are the coefficient of the artificial objective function. Presently, -1, -1, 0, which are the non-basic variable coefficients, 0, 0, which are the basic variable coefficient. They are the coefficient of the artificial objective function. Now, this table will keep as it is, but only the coefficient will change. Another thing, the artificial variables, their purpose is fulfilled. They are no longer useful. Now I can remove. I can remove A1 column. I can remove A2 column from the table. I can remove A1 column. I can remove A2 column from the table because their work is over. So I can remove these two columns. See, instead of removing, I am just putting all the coefficients 0, 0, 0. Everything 0. Okay, see here. Next table. Next table is like this. So next table, the A1 column, all elements are put 0. Nothing is there. Okay. All are 0. Because this A1 is artificial variable, no longer his help is required. Similarly, artificial variable 2, his help also no longer required because they are the non-basic variables. So that is the reason instead of removing, I am just making all these elements, all the coefficients. You can see all the boxes below A1, above A1, 0. Okay, this. However, the X3, X3 column and the elements 1, 0, 0, top of 0. So I am keeping as it is. Now we want to use the second phase objective function. So second phase objective function means we want to maximize Z. It has coefficients like x1 coefficient is 1, x2 coefficient is 3, x3 coefficient is 1. Okay. Now tell me where I want to put this x1 coefficient, x2 coefficient, x3 coefficient. So here this A1, A2 column we don't want to touch. The x3 above there is a 0. In the next table, this 0 you make it 1 because x3 is there. Okay, x1. See, instead of 1, 3, 1, if it is -1, -3, -1, also you can write accordingly. Here it is 1, 3, 1. The coefficients will be simply here 0, 0, 1. Then here 0, 0. Instead of 0, 0, it will be 1, 3. Okay, 1, 3. You can see here 1, 3. Now, once we have completed this, we like to fill up the last row of the table. You can see here 0, 0, 1 and 1, 3. See 1, 3, the A1 column, A2 column, they are not required. We are not bothering. So if we are not bothering, so we only fill up only one element. Which one? Below x3. Below x3. So if you want to compute 1, 3 inner product with 1, 0, what is the value? 1, 3 inner product with 1, 0, what is the value? Hello? Are you there?
1. It is 1.
1. 1 minus 1.
0.
1 minus 1. It is 0. Assume A1 column is not there. A2 column is not there. Okay, only one column. Okay, so this. So you can see here this is a solution. But there is no negative element. This is a solution. This solution is optimal. Optimal for what? Optimal for the final problem. Because the optimal solution of second phase equal to the optimal solution. Optimal solution of the first phase, not the optimal solution. It is the optimal solution of first phase. Okay, this. See, this problem you can see here, x1. What is that x1? So 1, 3 inner product with 8, 2. 1, 3 inner product 8, 2. So 8 into 1, that is 8 plus 6, 14. So the objective function value equal to 14. So what is the conclusion? X1 equal to 8, x2 equal to 2, x3 equal to 3, x3 equal to 0. This is a solution. Now, in this problem itself, so we find there is an option that this problem has some alternate optimal solution. Can you guess me what is the alternate optimal solution? If I am considering x1 equal to 0, x2 equal to 2, x3 equal to 8, we will find the same solution.
Yes, sir.
So now the question is how to detect that the problem has alternate optimal solution. So how to detect that the problem has alternate optimal solution? You can see here below x3, what is x3? X3 is a non-basic variable. In the indicator row below x3 there is a 0. This a1, a2 are not there. Don't worry about a1, a2 are not there. So x3, below x3 there is a 0. This 0 indicates there is some alternate optimal solution. Why? Because in case you find 1, 0 is fine. If it is 0, 0, it is not fine because you cannot divide by 0. 1, 0. So if 1, 0 is there, we'll take positive ratio. 8 by 1, 8. Okay. So what we want to do it, this x3 and x1. In the next table, we'll have to interchange. X3 will come to x1 position and x1 will go to x3 position. And there is a coefficient. You can see here x3, the top coefficient is 1. And similarly, so the x1 coefficient is here also 1. So we interchange. So next time you can see here what is happening. The problem x1 it has come to this case. So the coefficients are 0, 0, 1 and x3, x2. These coefficients 1, 3 and we have a solution. Another solution. Another alternate optimal solution that is 0 to 8. 0 to 8. And why it is optimal? Because earlier you got 14, now also 14. Same solution. So we have got two solutions. With respect to these two optimal solutions, this problem has infinite number of optimal solutions. Once we have detected 2, so this problem I can say here, see, that is 8 to 0, 8 to 0, and this is 0 to 8. Okay. For example, if I am considering something like say here 4, 4, 1, 4, 4, 1, 4. What is happening? 4, 1, 4, 4, 1, 4. Sorry, not 4. This is actually
4, 2, 4, sir.
4, 2, 4. 4, 2, 4. Okay. So 2 is common. Okay, 4, 2, 4. 4, 2, 4 is a solution. See, earlier you got 8 to 0 solution. Then we have 0 to 8 another solution. Now I'm saying 4 to 4. 8 plus 6, that is 14. So there are infinite number of solutions. The convex combination of 2, say how we have detected that is 4 to 4 because you sum it, these two vector, the column vector, then take the average. Okay, lambda equal to half. So lambda equal to half, say lambda times the first vector x1 plus 1 minus lambda times second vector x2 and put lambda equal to half. So this gives value like say 4 to 4, x1 equal to 4, x2 equal to 2, x3 equal to 4. If you put lambda equal to 1/3, you get another solution. Lambda equal to 1/4, another solution. There are infinite number of solutions. this linear programming problem has infinite number of solutions. Okay. The second example, very quickly I like to show you. Very similar. See, second problem. So what is the auxiliary function? You can see here. The auxiliary function equal to minimization type. First one is maximization type. Second one is minimization type. The auxiliary function coefficient, that is 3x1 plus x2 plus x3. Now, as you know, the first phase problem is common. Yes or no? The first phase problem is common. So this is the first phase problem. You can see here. First phase problem. Okay. So the first phase problem is common. So you can see here. And here also same mistake, that is minus 3 by 4. Okay. So finally, we have, this is the solution. That is the first phase solution. So what is the value of A1, A2? Presently in this table. A1, A2. They are non-basic variable, 0. Yes or no?
Yes, sir.
0. So once it is 0, the first phase is complete. So what we will do? We will replace, we will keep the same table. So the artificial variables A1, A2, these two columns you can remove, or the coefficient you can make 0. We are making the coefficient 0. Okay. So what is the new auxiliary function? Minima is z equal to 3x1 plus x2 plus x3. But generally we solve maximization type problem, not minimization. So always maximization. So minus z equal to minus 3x1 minus x2 minus x3. Now where to place? Where to place? So we'll place. So above x3, how much it will be there? Minus 1. Then in side by side, x1, x2, how much you can write? Minus 3, minus 1. Okay. After that, we will compute the table. So here we are computing the table in this manner. So minus 3, minus 1, and here the A1 column, A2 column you will remove. Only I have kept because some work we have done, so we want to keep as it is. Okay, x3. Now, how minus 2 has come to the picture? I am discussing here. Minus 3 minus 1. Minus 3 minus 1. Inner product with 1, 0. How much it will be?
Minus 3.
Minus 3. Minus 3 plus 1. That is minus 1, minus 1 minus plus. Minus 3 plus 1. How much it will be?
Minus 2.
Minus 2. Now, earlier, directly you are getting all were positive. It was 0, 0, 0. Now it is 0, 0, minus 2. Is it optimal? With respect to second phase of the function, is it optimal? Answer is no. It is not optimal because it is negative. So we need a iteration. So if you go for iteration, so you can see here it is possible. This x3 is coming to x1 position and x1 is coming to x3 position in the next table. In this manner, you can see here x1 and on the top there is minus 3, x3 inside there is minus 1, x2 minus 1, this. Okay, so we start the operation. See here it is very simple. So since in this table, if 1 is becoming the key element, you divide. So this value remain 8, no change. In the same column, you divide by 1 with a minus sign. This minus 2 is becoming 2. Okay. So only one change there you can find here. This minus 2 is becoming 2. So other thing remains same. And this 1 into 2, 0 into 8, this remains 2. And this value, earlier it was minus 26, you can see here. So next there will be, so you can see 1 into minus 26. How much? 1 into minus 26. Minus 26 plus 16. That is minus 10. So we got minus 10. So minus z equal to minus 10. So z equal to 10. So our optimal solution x1 equal to 0. Okay. x2 equal to 2. x3 equal to 8. So and optimal solution z star equal to 10. So now the question is there any alternate optimal solution? I will stop here. Is there any alternate optimal solution?
No.
Because in case of if it is instead of 2, if it is 0, then it is possible, you can say, but it is 2, a positive number, so there is no alternate optimal solution. So my request is this type of table you use. So now this table is convenient, and convenient in the sense you can solve all type of problem using this table. Okay. So first table, second table, third table. This third type of table, that is the condensed simplex table, you must use and solve always maximization type problem. If it is minimization, change into maximization. Now these two slides I will give to everybody, and for the two-phase simplex method, I will send you a series of problems for the homework. Will you do it? Solve the problem and keep it ready, so it may be useful. Okay, it may be useful to you. Okay, right? So thank you. So we'll stop here. So those are not getting my slide, please share your friend's slide, and or you can ask me, I will send again. But it is, I am always sending through ERP, so you will find in your email that slide. Okay, so that is convenient, and if I am passing no several times this that, you will face problem. Always please check your mail in case you are not available in the class, and you keep the track what is there, what I am sending, and maybe today or tomorrow I will make the slides and I will send. Okay, after some correction. Okay, thank you.
Thank you, sir.
Thank you, sir.
See, and be careful, and very quickly I am going to take a test. Okay, and that test is objective types. So maybe several questions will be there, and you will very quickly submit the answer. Okay, online. Thank you.